So today we're going to go over the last lecture on power electronics, and that will be three-phase inverters. This is an important topic for motor control later, especially for brushless motors, such as those used in drones. They use three-phase inverters when you buy those magic components that drive the motor. They use the ideas that we're going to see here. So as I said, this is the last lecture on power electronics, and from now on, next week, the focus will shift from power electronics to actuators, and things tend to get a bit easier for the second part. I will post the solutions to the second assignment today, and I will also post the new assignment today. We'll have 4 assignments, and so this will be the third one. So in this lecture, we're going to study the principles of three-phase inverters using the same ideas that we discussed in lecture 6 and 7. Control the voltage of a three-phase inverter using pulse width modulation, and develop a controller for a three-phase inverter. A very common application of three-phase inverters is for brushless motors, those used in drones, for example. A rough idea of how those work is just to put a magnet inside of a magnetic field. Let's say a magnet like that. And then you have 3 coils. They are shifted in mechanically and electrically by 120 degrees. Depending on the way we activate them, we can now create a magnetic field that points that way, that points this way, or points that way. And as a result, the magnet that is inside will align itself with that resulting magnetic field. The problem that we can clearly see here is that we can only have this vector pointing towards a finite number of directions in 6 different directions, which means that the rotor would have to jump from one phase to another, and the control would be a bit choppy in that regards because it's not very smooth. We can only have a resolution that is limited by the number of coils that we have inside of that rotor. So what is the solution here? How can we make the rotor go between different phases? And how can you create this magnetic field that actually rotates at a given speed and drags the rotor with it at a speed that we can control? Another application of three-phase inverters is for high power applications. For example, solar panels that will generate a DC voltage needs to be converted into three-phase AC at a specific frequency before they can be used in a power line transmission. So before we put them into the grid, DC will have to go through 3 different inverters shifted by 120 degrees. We then create a 3-phase AC, and this 3-phase AC, each phase again is shifted by 120 degrees, and then, only then, it can be applied to the grid. How can we do that? From a DC supply voltage. The idea is relatively easy to understand, but the way we calculate the duty cycle can be a bit complicated. The first attempt to design a 3-phase inverter would obviously be the use of 3 independent H bridges. Full H bridges, as you can see here. We have a DC supply that goes through 3 different inverters. Each inverter will now power a transformer. In this way, the DC and the AC output are decoupled. And this transformer could have any ratio that we want to apply to it. But the idea of using a transformer is just to decouple both sides of this circuit, the AC and the DC. And that would result into something like that. We have basically 3 H bridges connected to a load that is here. And this now, if you control each H bridge independently, we create that reference signal as we did in lecture 6 for sinusoidal waveforms, but now with 3 reference sinusoidal waveforms shifted by 120 degrees each. That would be sufficient to power this. Our job would be done, and the system would work with a 3-phase AC. The problem with this arrangement is that timing the signals is challenging. It needs to be very precise. And another potential challenge here is the fact that we would need 12 transistors, 12 diodes to create this 3-phase inverter. So the cost is significant, and also physically to implement the timing between the gates, the gating signal, that would be relatively complicated. So what is the better solution? Here it is. We actually can use we only would need 6 transistors to do that. And the difference compared to what we saw before is that we create now a common point for all these transistors to deliver power to with a balanced load. And this point here is the neutral point. So now we see one bridge inverter as the same we had before with this extra lag, Q6, Q2 on the right. And each bridge now powers a load Z. You see that the load is balanced. That's one of the assumptions that we are going to make moving forward. The load in a 3-phase inverter is always balanced. And now how can we control this? Well, now we need to create a path for the current to flow through each of these impedances, impedances that represent the load. We have a VCC DC power input. There we have 0 volts here, or negative VS. So this becomes negative VS. And you can now, based on how we control the transistors create different paths. For example, if you activate Q1, we can have a path to the neutral. Now the current needs to get out. It can get out from here, or it can get out from there. And this is one possible configuration. You see that a current flows through all branches of the load, and 3 transistors will now conduct at a given time instead of 2, as we had before. 3 transistors conduct at a time. The question that we're going to attempt to answer right now is, how do we time these transistors? What is the actual sequence or the combination of transistor activation in order to create something that resembles a sinusoidal waveform in the output, having 120 degrees phase shift between them? So there are several different methods to do this. The one that we are going to use in this lecture is the so-called 180-degree conduction, where we're going to specify which transistor in a lag conducts, and that transistor in a lag will conduct by 180 degrees before we switch to the other transistor in the same lag. There is also 120-degree conduction is just another example. There works very similarly. It's just the way we define for how long each transistor in a lag conducts. So let's see an example here. We have our H bridge with 3-phase inverter, and you're going to take one lag, let's say this one, and specify the time each transistor in that lag conducts. As we saw before, only one transistor in the same lag can conduct at a given time. If both transistors conduct at a given time, then we essentially created a short circuit. So either Q1 or Q4 can conduct, but not both at the same time. So now we are going to take our period, that it would be 2 pi radians here, and we are just showing these in degrees to make it easier, but this is the period of the sinusoidal waveform we want in the output, 2 pi. So it's frequency independent. And we are going to split that into different regions. Here we have 6 different regions, and each of them has a width of 60 degrees. We're going to let one transistor in this lag conduct by 180 degrees. That's why you call this 180 degrees phase. Let's look. We start with transistor Q1. So Q1 will conduct from 0 to 180 degrees. And transistor Q4, which is the other transistor in the lag, will conduct from 180 to 360. So half of the period. When transistor Q1 conducts, it's assumed that a transistor Q4 is not conducting, and when transistor Q4 conducts, transistor Q1 is off. Okay, and then you repeat this cycle on and on. Having that, we can now move to another lag. we can look at a leg, let's say 5 and 2, and apply the same logic. But now notice that we're going to shift this leg with respect to the previous one by 60 degrees. It will start at 60 degrees. If you look, for example, I think it's easier to see in the middle leg here, it is shifted by 60 degrees with respect to the first one. And leg Q2, Q5 is then shifted with respect to leg Q3, Q6 by another 60 degrees. And now we're going to repeat the same process. So we are dealing at this point with this leg here, Q5 and Q2. So let's start with Q2. Q2 conducts by 60 degrees, and then it's turned off. And then we have Q5 conducting. Then Q5 turns off, and we go back to Q2 and back to Q5. And again, Q1 here is Q1, Q4, Q1, Q4. Finally, you can look at the middle leg, apply the same logic. And for now, we go with Q3, and then we turn off Q3, we go with Q6. Q6 turns off, Q3 turns back on after 60 degrees. Then Q6, and then Q6. Okay, and this is now the timing of each of these transistors. We notice that at a given time here, 3 transistors are conducting. So from 0 to 60 degrees, we have Q1, Q5, and Q6. We are going to move on to the second phase, that is from 60 to 120 degrees. Then what happens? Q6 turns off and Q3 turns on, and you again have 3 transistors conducting at a given time. And then you repeat this cycle on and on. Any questions so far? No? Very well. Now, for reference, I've called these points here A, B, and C in the middle of the bridge. And they're all connected to the neutral. So now, depending on the combination of, or the phase of we are, we can specify the direction of the current flowing through each of the components in the load, and then also specify the voltage that we have across each of the branches of the load. So let's do that. Let's start with phase 1. In phase 1, we have transistors Q1, 5, and 6. Q1, Q5, and Q6. So current flows clearly this way and that way. That's the path we created in phase 1. So if you look at the other branches where the transistors are open, we can neglect them, and you can consider the transistors to be ideal and rewrite the equivalent circuit as shown. We see that we have 2 branches coming from VCC. They each feed an impedance Z. Then they meet at the neutral. And from the neutral to the negative side, we have another impedance Z. So the equivalent circuit is what we see in that picture. So the A, C, and B are these points in the middle of the bridge again. Is this conversion clear? Any questions here? See what these things are doing?
Could you repeat that again, please?
Which part exactly?
Just the whole connection and current and everything.
All right. Okay, so we have transistors Q1, Q5, and Q6. So transistor Q1 connects VCC through Z to the neutral because it's activated. And this corresponds to going from VCC through A, right, to the neutral.
Yeah.
Yeah. Now we have transistor 5 is also connected. So transistor 5 will go this way through C and to the neutral. So it would be this branch there. And then finally, we have transistor Q6. Q6 will now provide an output path for the current like that, and that goes to the other side of the power source. So this is this path there.
Okay, makes sense.
Okay, so we have current flowing this way from the power source through both impedances, and then flowing out of the neutral through the path that it goes through B. All right, so current here and there. What is the current? If you call this current the total current from the source, let's call this current I. The current from the source is the input voltage Vs divided by the total impedance. So the total impedance is the sum of this parallel impedance here, which is Z times Z divided by Z plus Z. This is Z squared over 2Z, which is Z over 2. Plus that other impedance. So the total impedance is Z plus Z over 2. That's the total impedance seen by the power source. So the current flowing in phase 1 is simply Vs divided by Z plus Z over 2. And when you solve for that, we get 2/3 of Vs divided by Z. That's the total current coming from the power source. Is this clear? Yeah? Okay. So if this is the current I1 flowing through the source, from the source through the load, we have 2/3 of Vs over Z. And now we can calculate the respective voltages across each branches of the load. Starting with point A with respect to the neutral, what is the voltage there? Is simply the current that passes through A, which is I1 over 2. The current passing through C is also I1 over 2 because they are in parallel. Yeah. And the current passing through B is simply I1. Okay. The current through the load, I1 over 2 times Z times the impedance, gives the voltage drop across the branch A. The current is what you calculated before, so you can replace current there and solve for the voltage. And when you solve for the voltage, you see that Z and Z will cancel out, 2 and 2 cancel out, and we were left with the Vs over 3, 1/3 of the input DC voltage. We can do the same for C. Is the same current and is I1 over 2. And if you calculate C, we find the same result, Vs over 3. Of course, it's the same in impedance in parallel with A, so the voltage must be exactly the same. What about the branch B? For branch B, we are calculating the voltage from B to the neutral. Notice that how B and the neutral are connected. The neutral has a higher voltage potential than B. The neutral has a higher voltage potential than B. It's 0, right? And the voltage across here is basically negative Vs, right? It's negative Vs. The effective voltage across the branch of the. I shouldn't say it is Vs. The voltage there with respect to the neutral is subjected to the negative side of this voltage. The voltage is negative. It's not necessarily Vs, but it's negative because you're measuring that the other way around. When you go from A to neutral, the voltage is positive, but you now go from B to neutral, the voltage is negative. Hence the negative sign here. So the current through branch B is simply I1, is not I1 over 2. The current that we calculated before holds, except that we now have this negative sign because the current is flowing from a lower potential to from a high potential to a lower potential, from neutral to the negative side of the power input. And when you calculate that, we get negative 2 over 3 times Vs, 2/3 of the input voltage. Is this clear? This is the voltage across that part. The output. Is it clear? Any questions here? No? Okay, so this is phase 1. Now we have 3 different levels. We have 2 branches that have 1/3 of the input voltage, and you have another branch that has negative 2/3 of the input voltage. Now let's move on to phase number 2. In phase number 2, we have still Q1 and Q6, but now Q5 is off and Q2 is conducting. So things have changed a little bit. We have Q1 to the neutral. We have Q6 right there. So that's B. And we have Q2. Like that. Okay. We basically now moved one of the impedance. The parallel branch is under A now. What is the total impedance? Is the same as Z plus Z over 2. Because the load is balanced, the current will always be the same. The current is still 2/3 of Vs over Z. Now the current is the current flowing through, put it this way here, through the power source. Let's call that I2. Okay, now we have I2 flowing through A, and we have I2 over 2 and I2 over 2 following through B and C. And you can recalculate the voltages in the same way we did before. For A with respect to the neutral, we still have a positive voltage. Now it's 2/3 of the input voltage. If you go from B to the neutral, B and C to neutral, we have negative voltages because they're flipped now. And following the same strategy we used before, we conclude that the voltage drops there are negative Vs over 3 and negative Vs over 3. Right? It's the same levels of voltages that we calculated for this mode here, but now they are flipped. So the top becomes 2/3 and the bottom that is in parallel is 1/3 of the input voltage with the respective signs. Is this all good? Any questions so far? No?
Sorry, I have a question.
Yes, go ahead.
Would these voltage relations hold if we were using the other transistors? So if we were using the other 3 transistors instead of these 3?
Which 3 transistors? I'm sorry.
So we're using Q1, Q2, and Q6.
Oh, yeah.
We were using Q3, Q5, and 4.
Yeah. So if we simply change the transistors under the assumption that the same transistors in a lag do not conduct simultaneously, then these levels of voltage are always the same. We can only have 1/3, plus minus 1/3, or plus minus 2/3 of the input voltage, assuming that the load is balanced and assuming that, again, only one transistor conducts at a given time in a lag. These are the all possible combinations of voltage. We can't do anything other than that. The question will become, where exactly is the 1/3? Is it positive or negative? Where is the 2/3? Is it positive or negative? But those are the only possible levels of voltage. I don't know if that answered the question.
Okay.
Does it? Because these
Yeah.
levels here, they will flip, of course, as soon as we change one of the transistors. This will completely change. Okay, but it will change in the sense that 1/3 will go somewhere else and 2/3 will go somewhere else. But the levels themselves are always these 4 possible levels.
Okay.
Okay. Now let's go to phase 3. It's the same idea. I think for now, you get it. Do you need me to do another one, or do you get the idea?
I do have a quick question.
Yes, go ahead.
The switching of the transistors, we are still controlling it using like the optocoupler or whatever from the full bridge rectifier. Like we would have an external switching mechanism that controls the switching of those transistors.
Yes, precisely. This logic that we are implementing here is a logic that can run in a microcontroller, for example.
Okay.
Or in early days, this could be implemented with an analog system. And then you create 3 low power gating sequence signals, and they will go to each transistor there, depending on which phase of this conduction we are.
Right. Okay.
Right.
Thank you.
Yeah. But the power from the load is, again, and that's the whole point of power electronics, the power from the load comes from an external power supply, right? Whereas something low power will trigger the gates. Okay, very well. So now we can move on to phase 3, same idea, but now again, the path is slightly different. And we can recalculate the voltages across the load for each of these modes. So we now have positive Vs over 3 and negative 2 Vs over 3. And we can keep going. We can do phase 4, same thing. You see that it's the same procedure. I don't think there's any need to repeat that. And you see that the levels we are getting at the output are always 1/3 or 2/3, plus minus, but now they're just switching places. You're just switching places. And we go now for phase 5. Same stuff, now same current, same levels in the output voltage, but again, at different places. And when you reach phase, this should be phase 6. Yeah, this should be phase 6. When you reach phase 6, that's the last one. And from now on, we are going to start repeating the sequence. And if you go to the next phase, it would be the same as phase 1. Right? So from now on, we are repeating the sequence. And we go back to square 1. Now, how fast we do this, how fast we go from 1 to 6 determines the output frequency. If you go fast, then you see that these levels will change faster, and eventually the output frequency changes faster. This indeed depends on the frequency we want in the output. That determines how fast we change these. In this specific case, I'm showing this in terms of omega t, not time. Time is the frequency, so that becomes radians per second, just to avoid references to frequencies that right now don't need to be specified. Okay, so these are all the phases we got. 6 phases, 6 possible combinations, and 6 possible resulting voltages combinations across the load. Now let's plot them. So instead of plotting the actual values, we are going to plot VAN over VS, or the ratio, and the ratio will be 2/3 or 1/3, VBN and VCN. So these are the line to neutral waveforms. Everything we calculated before, we're just plotting them here. And this is what we get. So this is VA, VB, and VC normalized with respect to the input voltage for each phase that we calculated before, phase 1, phase 2, and so on. And this is what we get. So this is starting to look like a sinusoidal waveform. If we have a rough approximation here, we see that at this, we calculate the average for a given period. I see that this is starting to resemble a sinusoidal waveform. And you can go with the second one too. Another sinusoidal waveform. And another sinusoidal waveform. At this point, they are not necessarily shifted by 120 degrees, but they are 100. They are indeed something that roughly resembles a sinusoidal waveform. Now what we're going to do is we can do line to neutral waveforms. We're more interested on line to line waveforms. So if you want line to line waveforms, you need to find the subtraction between them. So line A from line B waveform would be VA minus VB. Line to line between B and C would be VC or VB minus VC, and between A and C, then VC minus VA. And so we take the neutral away, and instead of looking to at line to line, we are looking at line to neutral. We're going to look at line to line waveform, and this is what we get. All right, for VAB is VAN minus VAB. So the voltage between lines A and B is the voltage between line A and the neutral minus the voltage between line B and the neutral. And then you again plot that for the exact same periods that we defined before. And here is what we get. Something that looks like a sinusoidal waveform. We can do line B to neutral. Sorry, line AB. Let's do AC. This is what we get. And BC. This is what we get. If we do that. But in this example here, we're going to do the other ones later. This, what we see is VBN, VAB. We are basically subtracting them. I believe I started this the other way around. Let me just double check what I did here. Yes. Sorry, I think I misled you here. I meant to say that this is VN, this is VB, and this is the result. All right. Okay, that makes more sense. This is the result. So VAB is the difference between them, and still that gives us roughly some sort of sinusoidal waveform like that. Now we can do VBC, so VBN minus VCN, same thing. And we can do AC. AC is A neutral minus C neutral, and the result is there. So the line to neutral and line to line voltages are shifted by 60 degrees. And the reason for doing that is that now if we plot all three line to line voltages, we're going to see that the line to line voltages are exactly shifted 120 degrees out of phase with respect to each other. The line to line and line to neutral are shifted by 60. But now if you combine all the line to line voltages, they always have 120 degrees out of phase. And we achieve the goal of having a three-phase inverter, three phases, each being shifted by 120 degrees. Okay. Any questions before we move on? No?
Sure, so can you repeat? You said the neutral to line is shifted by 60 degrees, and then what?
I said that the line to neutral and line to line voltages, are shifted by 60 degrees. If you now compare the phase shift between different line to line voltages, they are shifted by 120 degrees, as is expected in a three-phase transformer or three-phase inverter.
Okay, thank you.
Line to line. So if you look at VAC and VBC, or did we define that a BC? VBC, these have 120 degrees phase shift. Okay, and then we look at the other one. How did you define that? VAB, VAC, and VAB. That would be another 120 degrees. And then if you compare these two, 240 degrees. Okay. And that's the ultimate goal. All right, so that's it for the three-phase inverter. Is relatively simple because as far as mechatronics projects are concerned, there isn't really much complications there, but it's a good idea to know how these things work. Now let's see something a bit more interesting, more complex. If we take what we created before and try to power a 3-phase motor with that having each 3 phases and 3 coils, we run into a problem. Let's assume, for example, that we have 3 coils oriented like that. And according to the operating modes that we defined before, we only have 6 possible combinations of voltages that can be applied to this specific motor at a given time. And let's assume that when we add, let's say, when you apply a voltage to this coil, it creates a magnetic field in this way. When you apply a voltage to this coil, it creates a magnetic field in that way, and so on, and this way. When we add this all up, there will be a resulting magnetic field pointing in a given direction. Based on the fact that you can only have 6 possible combinations of voltages, this vector will also only have 6 possible orientations. Only 6 possible orientations. And now the question becomes, if we want a motor to rotate at a given speed, or we want the motors to go to a specific position, how can we overcome this limitation? And instead of just having these 6 discrete positions, we want, let's say, to control the speed of a drone, we want to have a resulting vector like that, and this vector is to rotate at a given speed omega. And it cannot go from just one of the 6 positions to another. That would be very limiting to drag the rotor around. We want that to be smooth. How can we do that? That's the idea of space vector modulation. It's an idea to now define the duty cycle of each coil to control the voltage better, the average voltage better, to get this resulting vector moving at a specific direction in time, and then drag that around so that it can move the rotor at a specific speed. So that way we ensure a smooth rotation in the motor. How can we do that? This is the idea. So again, keeping in mind that each of these combinations that we saw before represents a specific resulting magnetic field in the motor, and assuming that the rotor always orients itself with respect to that resulting magnetic field. There are only 6 possible combinations. We are going to add 2. 2 possible combinations are when all the switches are connected to the power source, the positive side or the negative side. So for phase 1, for example, depending on how we define the phase 1, we can look back at the bridge and see how the transistors are switched. And we call that mode 100. The reason it's 100 is this. We have these gates here that represent the transistors for A, B, and C. And when connected to the positive side, we are going to assign a number 1, the Boolean value 1. And when the transistor is connected to the low potential, we're going to assign that specific transistor the Boolean value of 0. So for this configuration, we have 1, 0, 0. So this is mode 100, which represents phase 1. When we apply phase 1, when you apply 100 to the transformer, to the inverter, then again, that will represent the resulting magnetic field from the combination of all these 3 coils that are mechanically, physically spaced 120 degrees out of phase, in the same way that the phases are shifted by 120 degrees electrically. So that's the resulting magnetic field. We can now go to a different mode, another mode that we covered before. And in this case here, specifically, we have A and B are positive, so that's 1, 1, and C is negative, so that's 0 for C. So that's mode 110. And when we are in mode 110, again, that will result in a specific magnetic field, the resulting magnetic field that points in that given direction. And you can continue to all 6 modes that we created before. So this, and that. These are all 6 modes that we created before, and we are going to add 2. this one, where all transistors are switched to the low potential. So what is the average, what is the voltage across the load in this case? Everything has the same potential, right? So the effective voltage drop across the load, and that also happens when you switch everything to the high side of the voltage. The voltage across the load on either side of the load is the same, so the voltage drop across the load is also 0 volts. Now you're starting to get it. Let's say we are working with these two vectors, 1, 1, 0, and 1 and 1, 0, 0. I can get any linear combination of these vectors by changing the duty cycle that each of these modes operates at. My duty cycle go between 0.3 on one side and 0.7 on the other side, then the average voltage will shift, the average resulting vector will shift and will now point more towards 1, 1, 0. If again I time the duty cycle between these two vectors to get 1, 0, 0 conducting for longer than 1, 0, 1, then the resulting vector may go like that. By now timing the duty cycle, we can get any linear combination of these two vectors and make the resulting vector, the average resulting vector, go between them. What is the mode 0, 0, 0 and 1, 1, 0 for?
Duty cycle completely on or completely off.
Exactly. So that's the one that is the dead zone. The duty cycle is off. You can now use them to control the magnitude. We can use them to actually control the magnitude if we pass through one of these values here. There's no transmission, so the average voltage decreases. And now we can also control the magnitude of the resulting vector, which before was kind of fixed. So by timing 1, 0, 0, 1, 1, 0, we control the direction. In the process, we may pass through states 0, 0, 0 or 1, 1, 1 to now lower the magnitude of the vector and control the magnitude of the resulting voltage applied to the rotor. The question now is, how is the duty cycle for this specific 1, 0, 0 and 1, 1, 1 operating modes? Is this clear before we move on? Yeah? Very well. So let's see how we do that. So here we have the resulting vectors that originate from each operating mode. We have 6 operating modes, same ones we calculated before. And we have 2 additional operating modes, 0, 0, 0 and 1, 1, 1. Those give 0 voltage in the output. And now let's plot this as vectors. So we see that the resulting vector from 1, 1, 1 goes like that. The resulting vector from 0, 0, 1, which is the complement of that one, goes in the same direction, that has the same direction but a different same orientation but a different direction. It goes now to positive C+. And 0, 0, 0 and 1, 1, 1 have a magnitude of 0, so they remain at the center there. Right? When we go, for example, with 1, 1, 0, we have this vector, and they're going to call that, no, that's not 1, 1, 0. This is 1, 1, 1, 0, 0. Direction A+. So the opposite, the complement of that would be A-. Now we have C+, the complement of that is C-, and so on. So now we have directions for each of those resulting vectors. Of course, it depends on how the coils are physically wired, but this is the convention that we're going to use moving forward. Okay. Now let's see what we do with this. Let's assume that the vector we want to create is the black vector. This is the position of the rotor we want. And then you're going to take that black vector and make that rotate at a given speed. We need to create that black vector. We don't have access to it. We don't have that vector in our discrete collection of possible vectors. We only have 1, 0, 0 and 1, 1, 0, 1, 0, 0 and 1, 1, 0. We now need to recreate that vector with a linear combination of other vectors. So here, one possible solution to that is to decompose that vector into 3. We have one component along 1, 1, 0, that is C minus. We have one component around A plus, that's 1, 0, 0, and you have another component around B plus that will connect the vectors together. And when we add them up, we go to the black vector that we specified before. So if this is vector 1, we can put the green vector here, and you can add the blue vector there, and we see that the resulting vector is indeed the blue one as a linear combination of the other 3. What did we use here? We used A plus. This is the magnitude we need in A plus. We used B plus. Here is the magnitude of the vector that we need along B plus. And we used C minus with the magnitude along C minus here. Now let's convert these magnitudes into this chart. We are going to use the same idea to create a duty cycle as we used before for in lectures 5, 6, and 7. We're going to have this triangular carrier signal, and now we're going to compare the magnitude to the strength of our reference signal with respect to the carrier signal's magnitude. Let's look at A, for example. A is positive, so A is positive, it goes on the positive side. This distance here from the magnitude here, the distance from the y-axis is exactly this distance. We can do B. B is also positive, and the magnitude of B is determined by this magnitude. Okay, and we can also do C. C is negative, so it goes on the negative side, and the magnitude of C is this C, and this is the magnitude of C. Now, how we create the black vector, or clearly we need to switch between the respective modes for A, B, and C minus, add a given a very specific duty cycle for each of them to have an average voltage that results in the black vector. So one step ahead now, once we have established the strength, the magnitude of all the signals and which ones we need, we can now do the comparison that we did before. Let's start with signal A plus. We are going to create a discrete gating signal QA that will correspond to A plus when all transistors are activated, 3 transistors are activated. And now we're going to compare A plus with the carrier signal. When A plus is greater than the carrier signal, we turn that specific mode on, and when not, then we turn that specific mode off. So from the beginning here, we have 0, and then you have this whole part here where A plus is greater than the carrier, so it turns on, and then during this period, it turns off and turns on again. We can do the same for B plus, only during this part of the period here, and that part, B plus is on, otherwise it's off. And we can also do C minus. We are looking at the magnitude, the sign also matters, and you see that only during this portion here, C minus is greater than the carrier signal. So we only switch on for this short amounts of time here. Now we have 3 specific duty cycles for them, and we can now look at which modes we need to operate. So let's look at the first one. The first one, A is 0, B is 0, C is minus is also 0. When you move on, now A goes to 1, B remains 0, C remains 0. Moving on to the next phase, we have 1, 1, 0. Once again, moving again, 1, 1, 1. And again, 1, 1, 0, 1, 0, 0, 0, 0, 0. If we now look at the first mode is 0, 0, 0. We need to go to 0, 0, 0 for that specific amount of time. After that specific amount of time, we go to 1, 0, 0. After that specific amount of time, 1, 1, 1. I'm taking this from 1, 1, 0. Sorry, 1, 1, 0. Taking this from these combinations here. Moving on, 1, 1, 1. This one. Moving on, 1, 1, 0. 1, 0, 0, and 0, 0, 0. If you now go through this combination, and we time these combinations according to the diagram that we have here, you see that this is a function of time now. The average voltage across the load is the black vector. And now if you move the black vector, we still decompose the black vector into other coordinates, readjust the magnitude of the signals, and recalculate the duty cycle. So now we can, by properly timing this, we can make the black vector rotate, or if you make the black vector rotate, we adjust the duty cycle respectively. Remember that this is happening very fast at a very high frequency. So now you have the ability to take that black vector and put that anywhere on the plane, anywhere on this 2D plane, and that will control. Now, if you have, say, a brushless motor, exactly how the brushless motor is oriented. If you change the speed of that black vector as it rotates, then you change the speed of the brushless motor. Any questions?
Yeah, one quick one. What does the circle represent? Does that represent the sort of the VS?
Yes, this represents the strength of the voltages available for each of these
Oh,
vectors.
okay. So, and then I guess our main vectors, the 1, 1, 0, those can't go more than the available voltage. Like,
not the available voltage per branch of the load, but when we add them up, we go to VS.
Okay.
Okay, let's do another example here. We have that black vector, and the composition of that black vector is given by the blue, red, and yellow. We don't need to go to the details how to do that. It's just boring algebra. And you see that to create the black vector, we can add them up here, and you see that that matches. So this is the resulting vector here, and then we add the blue, we go there. We add the green. This is the green one. We go there. So this adds up. And once this adds up, we now need to define the magnitude of each of the signals. We need B plus. B plus is positive. We need C minus. C minus, so negative. And we need A minus. And you see that the size of those vectors, the magnitude of those vectors, determine how far we are from the x-axis. We can now do the comparison with the carrier signal. For B plus, we see that a B plus is only on here and here. We can see that C plus is only on during this part and that part. And you can see that an A plus is only on here and there. Those are the only instances where the reference signals have a greater magnitude than the carrier. We find minus A plus B and plus C. We always list them A, B, and C regardless of the sign. And now we can find the sequences. For the very first sequence, we have 0, 0, 0. For the second sequence, we have 0, 1, 0. Third, 0, 1, 1. Fourth, 1, 1, 0. fifth, 0, 1, 1, 0, 1, 0, and 0, 0, 0. And we see that now we start to repeat. So I can take these sequences here, list them there, and that's the activation sequence that we need to create that vector. Once again, remember that these are timed. These are a function of time. So depending on the frequency we have, we know for how long we need to hold this state on. This state on, we will say hold by 1 microsecond. Then this state we have to be held by another 1 microsecond. Then the other one by a little more, by say, they are all 1 microsecond. Then they all have, in this case, all have the same. No, not necessarily. Then the next one by, let's say, 2 microseconds, and so on, right? This also comes from the chart that we implemented. Okay, and that's how we do speed control and position control in brushless motors. We're going to see brushless motors later, but when you buy your little device to control a drone that you magically plug it in and it turns, this is what is happening inside. Okay, and this is called the space vector modulation. Any questions? Any questions? No? All right, if there are no questions, we're going to do a quick exercise. This is not, it seems a bit complicated, but there isn't really, it can be a lot more complicated than this, but for purpose, in the context of mechatronics, this is more than enough. Let's do exercise 33. We have a sinusoidal phase to neutral voltage of the 3-phase inverter. They are shifted by 120 degrees. Calculate the line currents in the load due to the fundamental component of the output voltage. So this is powered with 244 volts. We have a balanced load. We are interested in the line current or the load current due to the fundamental component of the output voltage. All right, so let's get that done. Then the first thing we can calculate here is indeed the fundamental component of the output voltage. What would that be? We have a VCC of 244 volts. The fundamental component of the output voltage is 244 times 0.9 for a full bridge. And this is 219.6 volts. That's the fundamental component of the output voltage. That's what is available to the transformer, the inverter. Now, if you are interested in the peak volt current, yes.
How did you get 0.9?
From lecture 6. Fundamental component of a bridge inverter, for a full bridge inverter, is 0.9 of the line voltage. That's from lecture 6.
Oh yeah, true. I think.
Yeah. Whereas a half bridge would be 0.45. What is the peak current? Well, to determine the peak current, now we need to determine the voltage levels available across the load. What is the highest voltage level we can get across the load?
Is it
what is the highest? Two-thirds, exactly. Two-thirds of that, right? We would be 2/3 of 244, but because you're only interested in the fundamental component, that is 2/3 of this. So our peak voltage for the output would be 2/3 of VS, VF fundamental. So 2/3 of 219.6, and that is 144.6 volts. Okay, that's the voltage. Now we calculate the current for this voltage is easy. What is the impedance there? The impedance is easy to calculate. The resulting impedance is the sum of that impedance. So Z equals to 15 plus 6J omega. the magnitude of Z is the square root of real divided by the square plus the imaginary part squared. This is 8 point, how much is that? Can someone calculate this for me, please?
16.155.
55 ohms. And the angle of the output, the impedance is the arctangent of the imaginary part divided by the real part. And this is going to be 21.8. But because you have an inductive, clearly an inductive load, that is negative 21.8 degrees. Okay. That's the load magnitude, that's the load impedance angle. Now the first current for the first branch is this voltage at an angle of 0 degrees, that's our reference, divided by 16.15 with an angle of negative 21.8 degrees. Sorry, I made a mistake here. This is positive indeed. This doesn't make sense. The negative, this is positive, and when it goes upstairs, it becomes negative. So now we have 144 divided by that. That should be 8.9. And 0 minus 21.8 is negative 21.8 degrees. That's the first line current. The second line current would be IP2, 144.6 with an angle now of, depending on how we defined it, I defined it as negative 120 degrees. So behind the other one with the same impedance, magnitude, and load, which gives a peak current at 8.9. But now the angle changes to negative 141.8 degrees amps. And I peak 3 is the same input voltage. Now the angle is negative 240 degrees. Well, again, with respect to that, or 120 with respect to this, divided by the same 8.9, 21.8 degrees. So I peak 3 is 8.9 at an angle of negative 261.8 degrees amps with respect to the first.
Is that the right denominator?
Yeah, how come you're dividing by 8.9, not 16.515? For IP3,
sorry, that is, yes, that's 16 point.
Okay, thank you.
I actually put the answer here, right? See, I just accidentally copied the answer there. So this is 16.9, 16.15. Indeed. Thank you.
I still have another question.
Yeah.
How come you go the negative direction when you're like increasing the phase? If you go positive 120 to positive 240, is it the same thing?
Yeah, it's the same thing. It doesn't matter. Yeah.
But wouldn't that
It
change
depends.
the sign of your angle for your answer?
Yeah, it would certainly, but they will all still be shifted by the same amount. That's what matters.
Okay.
Right. These need to be shifted by 120. This need to be shifted by 120. This need to be shifted by 240. If that holds, then it's fine.
Thank you.
It's really a matter of how we wired the inverter. Okay, so you see this, all these complications, there's no need for us to complicate this more than that. I think what is important at this point is to understand how these bridges, these inverters work, and especially for space vector modulation, how later a brushless motor can be controlled using a DC supply. And that is quite interesting. I think this solution to the problem is quite ingenious. I have this vector rotating, which represents the orientation of the magnetic field inside the motor, and then we can beautifully convert that into duty cycles for the operating modes of the three-phase inverters. Is ingenious. And I think that understanding is sufficient. We don't need to calculate, to complicate this. any more than that. Okay. Any questions here? No? All right, so we can attempt, this exercise is very simple as well. We have a DC input voltage of 3-phase inverters, 400 volts, and the load is 4 ohms. The question is the instantaneous voltage levels of the line to neutral voltage, the peak current in each transistor. So what are the instantaneous voltage levels between phase and neutral? What are those levels?
Is it 1/3, 1/3, and 2/3?
It's 1/3, 2/3, plus minus. So we have either 0 or and 0. So that's done. And what is the peak current through each transistor? What is the peak current through each transistor? It's simply the current flowing through the load. Right? And the maximum current flowing through the load is the maximum voltage divided by the impedance. Let me do that quickly here. I'll only raise a little bit there. So for this second part, this is 33. This is 34. For 34, we have, it's a very simple exercise. We have the voltage levels as plus minus 2/3 of Vs, plus minus 1/3 of Vs, and 0. So plus minus 2/3 are going to give us plus minus 266.67 volts, and plus minus 1/3 is plus minus 133.33 volts from 400 volts there. And what is the peak current? Well, the peak current is the current that flows through here, through one of the diodes, the transistors, right? So let's say a current flowing through here, and this maximum current will occur when you apply the maximum level of voltage through that branch of the load. So the peak current is going to be 2/3 of Vs divided by the impedance Z. So the peak current is 2/3 of 400 divided by 4. Divided by 4. Yeah.
How come in this example we don't find the fundamental voltage by multiplying
Because
400
because the question didn't specify. It's just the peak current itself. It's everything combined. So that is 66.7 amps. Okay. So that's relatively simple. The examples that come out of this. There's no need to complicate this anymore than that. All right. So I'm going to stop here today. These are simple exercises. You can try this one on your own. I was practicing this and forgot to erase. You just need to note here that there is one vector missing. You need to find it. All right, so you're giving 2 vectors. The third one here is missing, and then you go to the decomposition of their magnitudes and then calculate the duty cycle. All right, so post the solution to this one later. You can attempt this on your own, and there is another one here for you to try as well. Okay, so that's it for today. I will fix the mistake with the quiz when marking. And as I said, this is the last lecture for power electronics. Now we are going to shift the focus to actuators. So if lecture 2 is still a bit fuzzy, I recommend that you go back there and take a look at the concepts of a magnetic circuit again before we start the next lecture, because you're going to use those concepts, right? And if you have any questions, you can book an appointment during office hours, or if all time slots are taken, just email me for an alternative time. All right, so have a good day, everyone. I'll see you again on Tuesday.